Okay, so the number of failures in 10 exponent 9 hours is a unit, and it is abbreviated as FITS. That is often used in reliability calculations. Now you are supposed to calculate the MTTF for a system with 500 components, where each component has a failure rate of 1000 FITS. Okay. Now the let's start with the first question. B. You realize that the failure rate is giving us 1000 FITS, which means that there is 1000 failures for every 9 hours, because that's the definition of FITS, right? Failure rate in 10 exponent 9 hours. Now, when you realize that if there are 1000 failures in 10 exponent 9 hours, then how many failures are there per every hour? Because that is what we are going to use in our calculations. So we have just normalized it to 10 exponent 9 hours, and that is just by dividing. Okay. So at the end of the day, we are going to have a failure rate of what? 10 raised to the power minus 6 failures per hours. Now, realize that the question asks us to calculate the MTTF of a system with 500 components. Okay. Now, we have to calculate the total failure rate. This is the failure rate for each component, right? So each component has a failure rate of this, right? It has a failure rate of 10 exponent minus 6. So to calculate the total failure rate of the system, then it's just the number of components times the failure rate. And now this is the assumption. The assumption here is that the system is connected in series. Okay. Now, if they were connected in parallel, probably the question would have said it. But I mean, they are connected in series for the most part, because it was silent on that. Okay. So I mean, it means you just have to add the individual failure rates. I mean, that's the general ideology, right? That when they are connected in series, then continue adding the general failure rate, and it's just multiplying by the total number. So when you multiply, you get 5 by 10 exponent minus 4 failures per hour. So that's more or less the total failure rate of the system. However, now we are supposed to calculate the mean time to failure. Okay. The formula is just 1 over the failure rate of the system. So you get 1 over lambda of system, and that's just 1 over this expression. So 1 over 5 by 10 exponent minus 4. So you get MTTF of what? 2000 hours. Okay. Now that's just part 1 of the question. Okay. Now part 2 says that if you add 2 redundant parts, so you realize that part 2 justifies the first part being in series, because the first part didn't talk about anything, but it says you're adding 2 redundant parts. Now redundant parts are usually parallel parts, such that each part can operate independently. Calculate the new MTTF of the system. Now first, let's understand the effect of the redundancy. The redundancy here means that the system will fail only if both parts fail, right? So 2 parts operating independently and are in parallel. The reliability of a parallel system is calculated based on the probability that all components fail. Okay. Now, it's actually a long proof. Okay, but the MTTF of 2 redundant parts is given by this. Okay, but for the sake of learning reasons, let's just prove it quickly. Now, from the Israel Corin book, it is clearly stated that a parallel system doesn't have a constant failure rate, right? Each failure rate decreases with the failure of each component. Now, you can prove that the MTTF of a parallel system with its models having the same failure rate, lambda, is given by 1 over k lambda. Summation of what? 1 over k lambda. Now, you see, our system here has 2 parallel parts, right? So in 2 parallel parts, and if you are going to sum from 1 up to n, right, of 1 over k lambda, it means that the first one will have just 1 over lambda, right? Where k here is 1, okay, and the second one will have 1 over 2 lambda. Now we just have two parallel paths, so that's it. Okay, there is actually a more rigorous proof. I don't know how to do that at the end of the video for if you want to watch it, but that's it, right? And when you add these two, you get 3 over 2 lambda. Okay, yeah, so that will be the total failure rate of the system: 1 over lambda plus 1 over 2 lambda. If there was a third one, to be 1 over 3 lambda, and it will continue adding. Okay, now once you realize that that will be your MTTF of the new system, you already know that the lambda of the system has been evaluated as what? As 5 by 10 exponent minus 4. Okay, so substituting into the formula will give you 3 over 2 multiplying 5 by 10 exponent minus 4, right? And that results in your final answer. So you realize that your new MTTF will be around 3,000 hours. Okay, yes, and you can just quickly check. Initially it was 2,000 hours, and adding redundant part has increased it to around 3,000. I think this figure is around 3,000, around 3,000 hours. So it's has increased it, right? So that just proves the answer as well, that increasing the redundant part also increases the reliability. And yeah, for the last part, probably let me add the proof. Now this is just the step-by-step proof, if probably you're just interested in proving. So you see, for a single component, right, this is the expression for the reliability: R e raised to the power minus lambda t, right? So for each of those 500 components in the question, each of them has more or less this reliability. Now, if the system is in parallel, right, we can only evaluate the reliability by first evaluating the reliability that the probability that the system fails, and we subtract 1, because reliability is just a probability function, right? So when you find the reverse, and yeah, you can just subtract 1 to get the failure rate. Okay, so the failure rate of each component therefore is just 1 minus e raised to the power lambda t, right? 1 minus the reliability. Now if you have uh two redundant paths, right, then it means that to find the reliability, you have to find that both of the components will fail, right? And you have to find 1 minus the probability that both of the components will fail, or else. So when you find 1 minus both the components will fail, it means that then that's the reliability that those components will not fail, right? This is just a concept in probability. So for both components failing, then we just multiply the failure rate, and when multiplying the failure rate, I mean, you come and get 1 minus e raised to the power lambda t all squared. Then the next part is you are supposed to find the reliability. You realize that here we are finding the failure rate of the two components, but now we have to find the actual reliability, right? Which is just 1 minus the failure rate of both of the components, right? So that's what you see. And when you simplify the expression, you come and get this one. Now, another formula from MTTF is just the integral from 0 to infinity of the reliability. Remember the definition of the mean time to failure. Okay, yes. So when you integrate from 0 to infinity of this expression, this is continual maths, but I'm very sure it's simple. So when you integrate it, you come and get something like what I showed in the previous slide, like this one. Okay, so here they broke the integral, integrated and everything, but I realized at the end of the day you get 3 over 2. Now it's just integral kind of thing that has been generalized by the Israel Corin book as that. Okay, that's when you have a stack of systems in parallel, right? And you have to find the total MTTF. It is just 1 over k multiplying lambda, right? And it's just the sum. So if you had 3 systems in parallel, the first one is just 1 over lambda, The second one will be 1 over 2 lambda. The third one will be 1 over what? 3 lambda. And yes, you can continue. But this is just for I think 3 systems. Now our question had only 2 systems. That's why I ended at 1 over 2 lambda. Yeah, and I think that ends this video.